I come to you from London, Ontario, Canada. You're used to the London of Europe. You might find it interesting that we also have a Thames River. We also have an Oxford Street, Queen Street, King Street, that all kind of run the same, just like your London, but we're not the real London. We do have very little rain, so that's one advantage we do have. I'm enjoying living the paradoxical life because I'm very excited to be here, but by the same token, I find it super intimidating when I think about the aggregate DNS expertise in this room. It's almost a little scary. So thank you for this opportunity. What I'm going to do today is just talk about how Zero Trust DNS, or Don't Talk to Strangers, has an implication of problems that are also resolvable. But thought you would be interested in finding out the types of things that are broken with this approach. But before we jump into that, let me do a quick review. I understand many in this room are already familiar with Zero Trust DNS. It's the concept where every destination must be resolved before the network path is even allowed. And we call it Don't Talk to Strangers at my company, and Microsoft's naming convention is Zero Trust DNS. And the aspect of it using a protective resolver is technically optional, but because it's a security focus, it's usually a part of that. And it can run either on the endpoint, like Microsoft does with ZTDNS, or it can run at the gateway, especially for endpoints that are not able to take an agent. Could be IoT, could be anything else. So then it's important for them to still have the same experience, the same protection, where the focus is on the egress side before it goes anywhere else. And there's just a quick diagram here that illustrates what the process actually looks like, where an endpoint will end up making a check literally for every single connection. Every TCP, UDP, any IP connection has to go through this check separately. So some of you might already be thinking through that this process is very intensive when it runs at the gateway, and it is. But in the end, the reason it's very efficient for the endpoint is that the endpoint gets that box number 4 at the bottom right, gets the reset packet when it is unable to make the connection. And that's what allows, for example, a browser experience that has mixed mode content. If there is content on it that's permitted by the protective resolver, but then maybe there's a tracker that goes to a destination of QDN that's blocked, that ends up being skipped very fast. So the net result actually is that you get a faster experience, even without like a uBlock origin or some kind of a tracker blocker. Now, for this to work properly, the endpoint DNS has to be enforced. So in my world, we live between the endpoint and the local caching resolver. Our product is the actual optimized on-prem caching resolver, and everything else is not permitted. And we can talk during the break later. Actually, Josh from Infoblox, we had a good conversation about that this morning. So even if a browser were to now attempt DOH like Firefox did when it first shipped with DOH by default to Cloudflare, if that attempt is made, it just simply fails and then does a fallback. Now, this approach is really good for network to vendors because it thwarts the typical threat actors model completely, that will use alternate DNS methods in order to circumvent protection mechanisms. But it's really bad for end users that then have an application that's broken, right? And that's what I'm here to share about today, how that is experienced. Once a source and destination pair is allowed by any protocol, then any port is allowed. And this is the same with our approach versus the Microsoft approach, unless it is overridden by an explicit block by port protocol or destination. And time-bound element is important to consider as well, because if you have zero trust, then there needs to be an end as well. So if we definitely forge or rewrite the TTL for any unreasonably long TTLs. And then outgoing connection rules are created ephemerally and literally get created and destroyed as the time to live varies on various FQDNs. So what does this approach bring? This is what the presentation is about now that we've got that background. When you take the approach of requiring every single destination to be resolvable first by policy, you have three classes of applications that break. And the first one would be legacy applications. So that would be anything that was written 20 years ago, that where the author put in static IP addresses in the application where it reaches the host. Or it could be hard-coded DNS servers at the endpoint. Could be hard-coded NTP servers that live to this day. A lot of new IoT devices in the industrial space are still shipping that way. I know there's a lot of standards coming out where that's supposed to be changed, but it hasn't yet. And then there's apps that are specifically designed to circumvent protective DNS. And those of us that live in the defensive or protective space are very familiar with the pains that it has been. While Telegram is an important platform to exist, it is also the most difficult one to block by network operators. Some of you may remember that story when Russia attempted to block Telegram. And in order to do so, they ended up having to shut down half of the internet to be able to block the method of them just popping up in various networks around the world. Retail VPNs, like ExpressVPN, for example, when you download the app, it preloads and pre-populates a list of IP addresses. So that is broken in this case. Any peer-to-peer application, and if any, are you familiar with the University of Toronto Citizen Lab? That's done really good work. They have Siphon as an app. So bottom line is this: if Siphon can get out of your network, so can the bad actor. And so that's our approach. And the second major category of applications that are broken with this approach is video, voice over IP. So it would be products like Google Meet, Zoom, Microsoft Teams. Oddly enough, what we've noticed the last number of years, a lot of these products have built resilience now, that if the direct by IP connections are failing, then they fall back to using FQDNs. And so it's, in a way, that's good to see, but we also understand that it would have been author reasons to do to bypass DNS altogether. And then the last class would be any time-bound expiries. So we notice, for example, in Outlook, if you have IMAP servers in Outlook, Outlook likes to just hang on to the time to live indefinitely. It just completely ignores whatever you give it. So to resolve this, our approach is basically to create an exemption by destination IP space, ports and protocol ranges. And this is also part of the RFC draft. I think I saw John Todd here before. Oh, there he is. Wow, even wearing red too. John and Tommy Jensen and I worked on this draft together to effectively create a standard for application authors to publish a service binding record to say, oh, we run this set of protocols at these trusted IP ranges, allow access to them. And so any app developers that we have influence over, we should definitely be recommending that they avoid DNS-less processes completely. So just a couple of other thoughts. Encrypted client hello, anybody who works in the defensive space, it's been very difficult for those that have relied on SNI in the past for security provisioning. But with this approach, you still have the full visibility while still having the better privacy and security at the same time. So it really is a win-win. And there's a couple of use cases that we can go through. I would say that I'll just jump to number 2. This has proven to be a super effective way of disrupting or never even allowing a command and control connection to get established to begin with. every advanced threat actor nowadays for the final C2 connection will not use DNS in most cases. There's actually been really good research from our Infoblox friends around that. And yeah, so bottom line is there's a way to leak-proof DNS-based egress control. And it just comes with some consequences that can be healed very easily. And as long as endpoints are forced to use a very specific resolver, this is all doable. But the greatest advancement has been that there's a strong anti-circumvention that makes command and control basically as impossible as you want it to be on a per policy basis. So I'll conclude there, and if there's any questions or comments.
Hi, thanks. Very interesting. Ray Bellis, ISC. So going back to that question of applications that don't honor the TTL, the draft you've talked about, have you said anything there about best practices, for example, on not caching the results of things like getAddr info calls to essentially require that apps should reacquire the host address every time they make a new connection, rather than caching one at the start of the application startup?
That is a good question. I would put that outside of the RFC because the RFC is really about creating a way for the IP address space to be discoverable using some method. And then whether that's time-bound or not would be up to implementation. In our case, we time-bound everything. In Microsoft CTDNS case, they've decided to not time-bound it.
Yeah, okay. I don't know whether this has been fixed, but I remember many years ago, one of the issues with Java applications in particular is that there's a standard Java call to resolve a host name, but then the JVM itself would cache those answers. So even if you actually asked it to request the host name again or to create a new Java host object, you just get the same answer back, and there was no way to actually force a Java app to re-inquire to the DNS to get that answer. So again, that would be an issue with those if that particular Java bug hasn't been resolved. It was a long time ago. But
yeah, thank you. Good comment.
Hello, Stefan Ubbing, SIDN. I was wondering how DNSSEC fits in this, because you mentioned alternating the answers, and DNSSEC doesn't work. And if an endpoint would like to have an AD bit, that might also has to be verified on the endpoint as well. Have you looked at DNSSEC in this?
Yeah, so in this case, our on-prem caching resolver is DNSSEC aware and will basically forward it to the fleet of protective resolvers that it forwards it to. And so that pass-through is still maintained.
Unless you alter the TTL.
In that case, we don't alter the TTL.
Okay.
Yes.
Yeah, thank you.
Thank you.
Hello, Klaus Deriller from nick.at. So if I understand it right, you only allow IP connections if DNS was used before. So if I have a malware, which doesn't make like malware.com lookup, the connection is open to the control server and it is allowed to connect. Or do you use a whitelist on the DNS server also to allow only certain DNS names to be resolved at all?
Yes, that is a very good question, because if, to use your example, if a attacker-controlled good reputation domain is accessible, then that C2 connection is allowed, right? So our approach is to take it deep defense in depth, but to always start with whitelisting. It's only at the very last step, when it's allowed, then it goes to a protective resolver. So the protective resolver really is the resolver of last resort. And in most cases, you have the most critical and high value assets in inventory that you'd put on a very strict whitelist where nothing gets changed. And in practice, we've done this long enough that we know that you can create it very easily, very quickly, and that stays static, doesn't work. And that's how you avoid problems like SolarGate, the SolarWinds stuff, supply chain attacks. Yeah.
Thank you.
Hello, John Todd from Quad9. A question on your specific implementation, because actually some of these questions have kind of triggered this in my mind. How do you deal with serve stale, or do you ever do serve stale, where you keep a record past its TTL because you're not able to connect to the authoritative server due to a network outage or anything else? Do you just expire it, or is there the concept of serve stale in your particular implementation? And then actually, how does serve stale factor in any of this for your platform?
That's a good question. I should have expected this coming from you, John. We actually currently don't support it. What our process is for resilience is to have a fleet of protective resolvers. So, for example, we'll have, as you know, we have Quad 9 on as a default. We have Cloudflare, the protective resolvers. We use clean browsing, a number of the other really good Anycast networks out there. And so if any one of them, as long as any one of them still serves it, it's good. So therefore, if you take care of the serve stale problem, thanks for having our back.
Okay, thanks.
Lars Eckert, Mozilla. I really didn't want to come to the mic at my very first OARC meeting, but I guess so. I really dislike this approach of let's break everything and then maybe unbreak some of it and we make applications jump through extra hoops so they can maybe talk to the internet. I work for a browser vendor, right? We see the tickets when applications break in the browser. You don't. So I guess the question is, how do we make sure that you see the tickets and not us?
It's a very good question. And I would say I would be very surprised if you got a single ticket from our client base. And here's why I say that. Right. Here's why I say that. As part of onboarding someone with zero trust, it's just like when we do incident response projects. First, we start with emotional empathy about the problems. Then we start with saying, look, things are about to get a lot worse before they get better. So it's about preparing them. It's about letting them know zero trust is going to be ripping off a Band-Aid and then getting them to work. But you can also do a smart thing, which is to do like adaptive learning for 3 months so that this doesn't happen. So for those reasons, I would say I'd be surprised if our implementation has.
So we see a lot of telemetry from Firefox, right? And I can show you Bugzilla tickets where we have managed deployments of things that are similar, where the user sitting in front of Firefox is angrily blaming Firefox for something that is due to security software that they didn't know their enterprise had installed.
Very well received.
Hi, Valentin Goshu, also Mozilla. So I find this difficult to work in organizations where you actually do need the web, because like if the website actually tries to resolve kind of a domain name where the authoritative server responds with an IP address, that's part of the question as well. So like you can ask it like, yeah, give me 1.1 and it responds with 1.1, and that kind of basically bypasses the whitelist, right? Because that would install that would allow a specific IP address because it's in the response, right? So it kind of you kind of need for this to work for the domain names to be part of a whitelist. Otherwise, it doesn't really work, right?
Correct, and that's why almost always it is associated with a whitelist.
Okay.
Together, yes.
Yeah. So in this case, but it doesn't really work in organizations that actually need a browser that's like you can browse to general purpose websites, right?
Well, it does work if we're getting into the nuanced stuff of what is a whitelist, right? And there's probably enough threat intel people in this group here that can break down the numbers. Out of the 1 billion domain names in existence, 600 million are actively being used, of which 100 million are in most graph databases, of which 10,000 is what a typical organization needs. So your whitelist does not need to be 1 billion. Your whitelist can just be everything that's been categorized, everything that's been tagged, everything we know about. That's still, from our perspective, a whitelist. So that's why it's practical.
Okay. Thank you.
Hi, this is Puneet Sood from Google. So interesting presentation. One question on a point you mentioned that you only keep an allow entry around for the DNS TTL, and there was something about serve stale. What do you do with the DNS TTLs, which are really short, like 0 second, 1 second, 5 second?
Well, we say the people at Google make a product called Chrome, and Chrome solved it. Chrome said, if you give me a 0.1 millisecond TTL, I'm going to rewrite it to 60. We do the same. Oh. So we have a minimum default which you can adjust, but the minimum default is 60 seconds.
Oh, thank you.
Rafael from the University of Twente. I have a question. Great talk, first of all. How this doesn't break a really large network layer? I mean, if I'm an attacker and I want to break this, I will just start to push like millions of IPv6 address in your filtering table, and you have to deal with that. So how do you handle with an evil attacker that can do this?
I don't know how you would populate it with million IPv6 addresses. They'd all have to come from a domain name that was allowed, that was whitelisted, right?
Okay.
And that's the reason, right? So for example, you don't want to whitelist nip.io. Those of you familiar with nip.io, yeah, that's not part of your whitelist. Okay. And we have a blacklist that overrides whitelist. So if someone by mistake puts in something like nip.io, it's a part of a blacklist that overrides it.
Thank you.
Patrick Pacek, ISC. I want to comment on the browser folks having been here for the first time. Please come and talk to you and us. Yes. Because I'm from ISC. We don't do any filtering, but we've proposed this method and experimented with it like 1 month after Firefox came with the announcement that DOH will be enabled by default. So perhaps we need to talk. Thank you.
Thank you. I second that.